Welcome to this tutorial on how to get an IDS camera working with the Beam Inspector open source beam profiling software. On the physical side of things, you need, for one, the beam profiling camera. In this example, what I'm showing here, there's already a tripod mount adapter plate attached to the camera, which is linked in the video description. In order to avoid overexposure, we need to attach a neutral density filter, in this case a ND 4.0 filter, to the camera. The camera thread is typically a C-mount thread, and the filter thread is typically a SM1 standard Thorlabs thread. For that we will use an adapter ring. Link is also in the video description to attach the filter to the camera. To mount the camera, we will use the thread plate. If you're in a metric country, you need to use a 1/4 inch to M6 adapter. Screw it in the tripod mount. Then you can attach a standard 1/2 inch Thorlabs post with a post holder, such that you can place the camera on the optical table. To get the signal to the PC, we will use a USB 3.0 cable and screw it tightly to the camera to make sure that it doesn't get accidentally disconnected. This concludes the mechanical assembly. Now for the electronics part, it's absolutely paramount that you use a proper USB connection, which means a proper USB cable and a proper USB port on your PC or laptop. You need to make sure that this USB port is capable of USB 3.05 gigabits per second transfer rate. The camera does not have a reduced signal rate mode. It simply will not work properly if you use a USB port that has a slower speed. Do not use any USB hubs or passive extension cords between this plug and your PC. We experienced a lot of issues with those. If you need to place the camera further away from the PC, we did test a few active USB expansion cords. For example, this one. I will put the link in the video description to the 3 meter and 5 meter variants. Those are active extension cords and should work. However, it's still recommended to directly connect the camera to your lab PC. Now we can jump to the lab PC and open Beam Inspector. And we can see that the camera already shows up. It's designated by its model name and the last 4 digits of the serial number. If the camera does not show up, if you only see image, which allows you to load a static image, you can simply hit the refresh button and the camera should show up if it's properly connected. Let's launch it and we see a signal. Now let's guide a laser beam onto the sensor. Now in this picture I'm sending a 10 milliwatt laser beam through the ND 4.0 filter onto the camera, and we can see that the picture is quite overexposed. We will fix that in a second. Before we start, let me introduce you to the navigation in Beam Inspector. You can zoom in and out of the picture with your mouse wheel, and you can pan around the picture by holding middle mouse button and dragging. There's also this button here on top, which allows you to reset the field of view such that the image fills the available screen space as best as possible without cropping any information. In order to control the exposure, we need to look on the right hand side under control. This pane may be hidden under device control. So if it's not there, simply click the device control button. And in this case, we need to reduce the exposure time since the image is fully overexposed, as we can see here with the solid red color. In order to do that, we can simply type the required exposure time. For example, now I'm trying 1000 microseconds, 1 millisecond, which is still not enough. So I want to be faster. In order to do that efficiently, I can simply place my cursor over the field for the exposure time and use my mouse wheel to scroll and adjust the exposure time until the image is not overexposed anymore. The exposure is affected by multiple parameters. One of them is the exposure time. A second one is the gain setting. There's an analog gain, which makes the image brighter, and a digital gain. Digital gain is not supported by every camera. If it's supported, it will be available under digital gain. You can also adjust the frame rate. In this case, the maximum frame rate that the camera is capable of is 10 frames a second, but you can also reduce it, for example, to 4 frames in this case. If you adjust the exposure time such that it becomes too long for the frame rate to keep up, you will start to see the frame rate reducing. If you now go back again with the exposure time to lower values, the frame rate won't increase automatically. And that's what this lock frame rate feature is for. So you can simply set the frame rate and lock it, and the software will always try to adjust the frame rate as close as possible to, in this case, 8 frames per second. Now on the left-hand side of the screen, we can see the results panel, which shows us the beam width, ellipticity, as well as the center of the beam, the centroid of the beam, relative to the 0, 0 position of the camera sensor, in this case in micrometer. We can also hide this panel if you want to have more screen real estate, and go to View, Plot Beam Info to show the most basic info directly in the image. We can also change the color map under View Color Map. There are different presets that you can choose from, or you can import your own color map under Load from File. You can also disable the beam evaluation by simply hitting the raw view, which shows you a raw picture of the camera sensor without any calculation or corrections applied. In case that you need to crop out some area of the sensor because you have some stray light hitting the sensor, or your beam is very small and you want to make sure that the calculation works correctly, you can apply a region of interest with this button. This will only be active if you're not in raw view mode. So I need to disable raw view mode. I will get the dashed box, which is the region of interest, and the calculation and everything will only be carried out, or the beam evaluation will only be carried out within this box. I can hit this button, Edit Region of Interest, to modify where this region of interest lies. I can click and drag to pan it. I can grab the edges or the lines to change the size. And once I'm done with my edit, I can simply hit the green check mark to apply the changes. Now, if I use the region of interest, there's a second button next to the Zoom to Sensor, which is Zoom to Region of Interest, which does the same thing, but simply zooms to the region of interest. One important note: whenever you take a beam profile measurement, make sure that you do not overexpose the sensor. So, for example, now the software calculates that the beam has a diameter of 2.4 and 2.4 millimeters on the major and minor axis. However, if I simply overexpose the beam, this value will go up to some arbitrary number. So whenever you take a measurement of the beam dimensions, make sure that you do not overexpose the sensor. It's better to slightly underexpose it than to overexpose it. If you want to get an idea how Gaussian your beam is, you can hit the Profiles View button. and it will show you a fit to the cross sections in X and Y directions directly through the beam. If you want to measure the positional stability of your laser, you can enable the stability view, which over time will track the centroid position, show a plot in X and Y versus time on the left hand side, and a 2D histogram on the right hand side. If the camera is running in a faulty state, it can look like this. So for example, now I plugged the camera deliberately into a USB port that does not support the full bandwidth. You will simply get an orange indicating light on the back of the camera. Now I plugged the camera into the correct USB port with 5 gigabit per second capability, and you see that the status indicating light in the back of the camera shows me a solid green light. That is it for the basic introduction into Beam Inspector.